Yeah, it's great to be here. Everybody's so enthusiastic about the research and really great energy in the room. So many thanks for the invitation, Robert and Sonia. So today we'll talk about long duration energy storage, and I would like first to say that we are equally enthusiastic at Imperial about energy research. We have a passionate group of researchers working at the Electric Power Innovation for a Carbon-Free Society Center, and the center really has a very broad scope. So colleagues are working even on stability issues, others are working on decision tools that could support net zero power systems, and myself, I'm working more on the services and the techno-economic pathways for the decarbonization. And particularly, we have ongoing work with 3 PhD students. You will all recognize Ignacio. So if you want to know anything about demand-side flexibility in Great Britain, your go-to person is Ignacio. He knows the ins and outs of demand-side flexibility in Great Britain, has reviewed all the pilots that were done in the last decade. And we have Guillaume, who is focusing on network-aware reserve procurement. So he knows all about networks, and Adam is working on long-duration storage. And the work I will present today is actually in collaboration with Adam, who is a PhD student, Andreas, who was a master's student at the Energy Futures Lab, and now he's doing a PhD with Pierre Pinson and Fei Teng, and Professor Green. So this work draws on 3 papers we have. 2 are released as preprints. The other one is currently under review. Oh, sorry, it says to be submitted. It's actually under review. And this is the outline for today's talk. So I'll start by giving you actually a brief update on the progress to net zero for the UK. Just because we're in Austria, and I think it might be interesting for you to see what's going on over there. Then I will describe the need for long-duration energy storage, just to make sure that we are all on the same page on what long-duration energy storage is supposed to do in a net zero system. And then I will move on into the more interesting problems of missing money and missing risk markets and how they affect the integration of long-duration energy storage. So with that, let's start with the targets. So the UK is one of many countries that has a net zero goal. This net zero goal is actually in legislation. So the aim is to reach net zero by 2050. And what is particularly unique about the UK, it's in a subset of countries that actually have a very detailed plan on how to reach net zero and have regular monitoring by the UK Climate Change Committee that tracks the progress to net zero and also offers several recommendations. So the few slides I have next are from the Climate Change Committee report, basically the 7th carbon budget. And this is a nice graph that makes us cautiously optimistic because you can see the greenhouse gas emissions from the UK all the way from the 90s to historical levels are about to 2020, then it's all projections. And you can see that we have almost half of the emissions we had in the 90s in the 2020. So how these reductions were actually achieved. You can see here another nice graph by the CCC where they look at the period starting from 2008 to 2022, and they see, okay, more than half is actually achieved from the energy supply, which is the yellow bar in this graph. And this is quite obvious when you look at the map. These are the maps with the power plant sites in Great Britain. And basically, you can very quickly spot that we have a lot more light blue dots, which are the wind power plants, and a lot more solar power plants, which are the yellow dots. If you are really observant, you can also see that the black dots have disappeared. I think there is only one in the 2023 map. There would be none today because the black dots are coal power plants, and the last coal power plant retired in September 2024. So this is the progress we have achieved to date and how the future looks like. So it looks like going all the way to 2050, the reduction in greenhouse gas emissions will keep coming from the energy supply. So you still see some contribution from the yellow part, but what you actually observe is that this yellow part is getting smaller and smaller because now we have to achieve reduction in greenhouse gas emissions from other sectors. And particularly, we see a very significant contribution from surface transport and also buildings, which actually is quite obvious this is a graph from the National Energy System Operator, where they see rising demand for electricity because the transport switches from oil to electricity and the heating switches from gas to electricity. So this is the general context in which we operate, and we have the two trends as everywhere else. We have decarbonization of the supply and electrification, which means rising demand, which leads to a dramatic reduction we want to achieve in the greenhouse gas emission intensity of electricity. These numbers are all based on the projections for this average hypothetical year from the CCC. So that's why the 2025 number might not match exactly the historical, but the main message is we are really talking about a reduction from the order of the hundreds of grams of CO2 per kilowatt hour to 1 in 2050. So this is quite an ambitious goal. And if you look at the system operators plan, this is not exactly a plan, it's more of a pathway because they don't really control the investments in generation. What you see though, it's a lot of new assets. And particularly, I would like you to pay attention to the pink bar, which is storage. So we see a lot more storage coming into the system, and some of this storage is actually long-duration storage, and some of it is in the form of hydrogen. The particular projection for hydrogen is in the order of 100 hours for 2050. The hydrogen is the blue as well. And what is really the storage that is included in the system operators plan is multiple types. We have new pump hydro storage, possibly compressed air energy storage, liquid air energy storage, but also hydrogen. And this is a graph from Ian Staffel's book where you actually see that he groups all these technologies, and basically, the long-duration storage is the types of storage that have very low energy-specific investment costs. Because anytime we start talking about long-duration storage, we go into that debate, should it be 8 hours, should it be 12 hours? Actually, we're really talking about the technology that has very low energy-specific investment costs. So with the context set, so where we are, we want to have a system that have a very low emission intensity, and quite likely this system will have a new type of asset, long-duration energy storage. Let's discuss why we actually need it. So we have a stylized GB system, so we don't run cases in the same models as the system operator because we're more interested in qualitative insights. So we don't necessarily want to find the specific numbers, but more of what are the mechanisms and the behaviors we observe. In this case, we have a single node system, greenfield expansion. We have scaled down the system to 100 megawatt, but have similar mix. And very importantly, we have 40 weather years because the interannual weather variability plays a very significant role on driving the needs for long-duration energy storage. We have different technologies, solar PV, wind, batteries, LDS, and CCGT with carbon capture. And you will see that we have different emission limits. So what we see here is that as the emission intensity gets lower, this is where we actually invest much more, both in wind and also in solar. And you will also see that the duration of this storage increases. So as we go to the very low levels of emission intensity, this is the case where we get this storage that is in the order of hundreds of hours. The 0.1 case is an extreme case. You saw earlier that the 1 gram is where we're aiming for the 2050. And what this storage does, if you look at basically the demand is the black line, the wind here is the blue, and the solar is the yellow. You see that we have this profile where we have abundant VRE supply in some periods, low VRE supply in others. So it feels natural to just put long duration energy storage here and just charge this storage in the periods we have abundant VRE and discharge it when we have very low VRE supply. So it all looks pretty straightforward in a system with a very large set of renewables that will put this long duration energy storage. And even if we look at the prices that come out of this model, the prices are on the right, and on the left you see the pattern for charging and discharging the storage. You see actually that we charge when the prices are low and we discharge when the prices are high. So LDS would make money. There's really no need to actually worry about it. But the truth is that in this particular model and in the models that we use to identify the needs for long duration energy storage, the prices can rise up to the value of lost load. In practice, in Great Britain, the prices don't rise all the way up to the value of lost load because we have a price cap. So once we have a price cap, basically you will see the spikes disappear. So we will have a well-known problem in electricity markets, which is called the missing money problem. And how does the missing money problem look like in this deeply decarbonized system with long duration energy storage? We have done the calculations, both for the case where the prices can rise up to vol, just to make sure that we have cost recovery in this case, as we would expect, that the revenues we get from the market would be enough to cover the costs. And then we took what I will call the baseline portfolio and dispatch it under a price cap, and this is the case where we actually start missing money. So the money we see from this energy market are not enough to cover the costs for these technologies. And you actually see that for solar and wind, the problem is not really acute because they don't really rely a lot on the scarcity periods for getting their revenues. But when you look at peakers, CCGT here is a peaker, and the storage, they actually miss money in double digits, so several percentage points of their costs. So the problem exists for years. The solution that has been proposed and implemented is actually to not have just an energy-only market where the prices rise up to vol, but we have this energy market with the prices rising up to a cap, and then we introduce a capacity market where we have our system operator who is releasing a demand curve for a capacity market, and then resources participate with certain capacity credits. Okay. So if we have this market, obvious question, why the long duration energy storage doesn't participate in it, and if it participates, will it actually recover its money, and will the system reach an optimal portfolio? So to participate in this market, we need to estimate the capacity credits for the storage. And the interesting thing about long duration energy storage is that it's honestly a system of components where you can independently size the energy capacity and the power capacity. So here is an example from a liquid air energy storage demo, and you clearly see that the energy capacity is the size of the tanks, and the power capacity is the capacity of the generator here, of the turbine. So if we want to do a good job in estimating the capacity credit, we actually have to consider different combinations of power and energy capacity, and basically we estimate the capacity credit for different durations. So these are results that the system operator has, where you see that they have calculated the capacity credits for different durations with increments of half an hour, but they reach all the way to 11.5. So what we did here, we followed a marginal accreditation method where we took our baseline portfolio, we dispatch it first under the price cap, we get what we call here an energy unserved note, for the expected unserved energy under this baseline portfolio. Then we go ahead and we put a marginal capacity of a perfectly reliable resource. This is the expected unserved energy we get with this marginal perfect resource. So we have our denominator, what would be the marginal maximum impact by adding a new resource. And then in the nominator, we actually go ahead and for every resource we consider, we add a marginal contribution and track this difference. So we calculate this capacity credit as the ratio of these two deltas in the expected unserved energy. Obviously for the storage, when R is the storage, we do this multiple times for different durations. And doing this multiple times for different durations, we actually see that we actually have a good concave curves. So there are a few observations from these slides. The first observation is that as the emission intensity gets lower, the capacity credit curves go to the right. What I mean by that, if, let's say, we take a look here at the 50-hour long duration energy storage, you see that in the green case, which is the 5 grams of CO2 per kilowatt hour, its capacity credit is much higher than in the gray case, which is the 1 gram of CO2 per kilowatt hour. The other thing we observe is that if you compare the two graphs to each other, the battery versus the long duration energy storage, again, let's just pick 100-hour. It doesn't really make sense to have a 100-hour battery, but for the sake of it, if we say we pick a 100-hour battery, you see that the capacity credit would be much higher for the battery compared to the LDS, and this is because the battery has higher round-trip efficiency. So these are the two observations we have for the credit. The reasons we calculated these curves is because we want to put them in a model that has a capacity market and let that model independently size the power and the energy capacity. So this is our setup where we have these different investors in generation assets, investors in storage assets, and also the consumers who have a demand curve. And we have three different markets: the energy market with a price cap, we have our capacity market, and we have an emissions market, because that's how we put the limit on the emission intensity. And having this set up, we run three different cases. The EOM vol run is the run from which I have presented results up to now. So this is the utopian perfect run. I guess economists favor it if prices could rise all the way up to vol. Then we have the energy-only market run with a price cap, where we have put a price cap, but we have decided to do nothing about the price cap distortions. And then we have the energy plus capacity market run, where we have the price cap in the energy market, and we have decided to introduce a capacity market, or in the case of GB, keep the capacity market we have. So what do we see? First, this is a graph where we discuss the results in terms of expected and served energy. And we saw these bars in relative terms. So 0 here would mean that we have the same expected and served energy as our perfect run, the EOM vol run with the baseline portfolio. So and then the blue bar is for the energy plus capacity market, and the red bar is for the energy-only market with a price cap. So the lower the bar, the better we do. We have similar levels of reliability as we have for the market with the prices rising up to vol. What you actually see is that the blue case does really well. We see very, very small heights in the high emission intensities, but as we go to the lower emission intensities, actually we see the results diverging more from this perfect run. And one reason for that is that, okay, the capacity market can really help with missing money, but it cannot really bring back incentives for the storage to charge at all times to avert expected and served energy, because the storage would really charge only at prices that are below the price cap times the round trip efficiency. It doesn't make sense. If you put it in an operational model, it has to charge at that lower price. But in the case of the EOM vol run, which is our perfect run, you see that we have a few hours every year that the storage was charged at higher prices than this threshold. So these incentives for charging disappear in the case where we have a price cap. So this explains to some extent our expected and served energy. Obviously, we got interested in the social welfare as well. Again, we saw the social welfare relative to that perfect run, so 0 corresponds to the same social welfare as the expected, as the energy-only market with vol. Again, here, similar behavior. The blue bar is quite low for the high emission intensities, but is relatively high for the lower emission intensities. Part of it is explained by the results we already saw on the expected and served energy, because we have more expected and served energy, so we would expect that we will see a hit on the social welfare. But we did an additional check where we actually compared the results in terms of the social welfare we get from this energy plus capacity market run, the blue run, to the social welfare we would get if we dispatch our baseline portfolio, which is the gray bar here, under the price cap. I will start with this case because this case is the case we are happy about, because what we see here is that the baseline portfolio would actually lead to a lower social welfare because it doesn't have the right mix for dispatching in an environment with a price cap. While what this portfolio does, it has adjusted the mix of investments so we can have an efficient dispatch in an environment with a price cap. So this is the case we are happy about. These cases, I would say the differences are relatively small, and we have different input assumptions in all this. So they don't seem material, but this difference here has made us thinking, because what we see here, why we find this case particularly interesting, is that the energy plus capacity market found the portfolio that performs worse than the baseline portfolio. And in this case, we start wondering why the model didn't just invest in the baseline portfolio. So we did an extra calculation where we calculated the capacity credit that that baseline portfolio would require to enter the market. So in this case, we assume that in the long run, all technologies in the baseline portfolio make their money from the energy plus the capacity market. The capacity credit of a reference technology is 1. The capacity market has a single price per accredited megawatt. And we calculate this required credit for the baseline portfolio simply by having this ratio. We have the missing money for the reference technology in the denominator and the missing money for the technology in question in the numerator. And what we actually see is the estimated credits, the credits we have seen so far with the marginal accreditation methods, are quite close to the required credits for all cases except our tricky case here. And this actually motivated us to think that in this case, we might be constrained in terms of the fuel, let's say, of the energy storage, that we might not have had enough time to recharge the storage between scarcity events. We did this calculation where we actually saw how many hours we had unserved energy and we had storage technologies not discharging at their maximum level. And you actually see that we have a few hours like that in all runs, and we have them also particularly in the 1 gram of CO2 per kilowatt hour case. So that made us think that when we are doing the marginal capacity accreditation for all these technologies, we might actually have accounted for contributions of storage to the reference technology. Because what it means here is that we have the storage there, we have the power capacity, but that storage is not charged enough to contribute to the adequacy. So we did an extra check where we actually adopted different dispatch assumptions for the storage in the marginal accreditation case. The unconstrained case here is the case we have been following so far. And now we did another extra run where we fixed the charging of the storage. And we see here what we expected to see, which is that the expected unserved energy just from this marginal perfect resource is much higher when we allow for the charging patterns to change. So this means that this marginal resource charges the storage, and then the storage contributes further to adequacy. So this is now where we are in terms of this research, that we have basically seen that the capacity credits for storage, of course, depend on the duration of the storage and characteristics like the charging efficiency. They significantly change for the portfolios with different emission intensities, and we see a sensitivity to assumptions about the storage charging. And we see that it's quite complicated to attribute the expected unserved energy to a particular technology. So we're doing some work on that, testing alternative assumptions for the accreditation methodology. But overall, I would say we still see that the capacity markets with these well-calibrated capacity credits definitely help us achieve a much better social welfare compared to a case we don't have a capacity market, both in terms of welfare, but also in terms of expected unserved energy. And next, we did another study where we started looking at missing risk markets. And the motivation for this work was that we had a long period in the UK where we didn't build any long-duration energy storage. So that's a question. When do you think we build the last long-duration energy storage in the UK? 60s.
This is compressed air energy storage, or is it some hydro storage? What type of storage is it?
It's pumped hydro.
80s.
Okay, good. So it's 83. And basically, we have 4 of these plants still operating. They were built between 63 and 83. To be very precise, between 83 and now, we had some pilot projects. So there was a competition from the government to test new technologies like compressed air energy storage and liquid air energy storage, but these projects are quite small, compared to the projects that we see here in terms of the pump hydro. Basically, this motivated an entire evidence-gathering process from the government because they say, okay, we see the long-duration energy storage appearing in every net zero pathway we do, but we also don't see the long-duration energy storage appearing anywhere in the connection queue. The question the government had was, are there barriers? What are the needs for long-duration energy storage? What are the barriers to actually deploying long-duration storage? And what are interventions that the government could take in order to accelerate the deployment of long-duration energy storage? And this process actually started in 2021, and I'll come back to this again later. But basically, by collecting responses from hundreds of stakeholders, the government identified different barriers, high upfront capital cost with long lead times, lack of track record for the new technologies, lack of revenue certainty, and lack of market signals. And I have highlighted the lack of revenue certainty because this is the barrier that the government decided that they have to address through intervention. And this is also the barrier that our model can give some insights about. So from the previous model we saw, we can also get the points for the 40 different weather years of how much net revenue the LDS would make. And you actually see that there is quite a wide distribution. In expectation, in all these cases, the investors get back the risk-free cost of capital. We are operating in a risk-neutral environment, but you see that these distributions are quite wide, and some years we might make 300% of our annualized fixed cost, and other years we might lose 50%. So this all makes sense based on the weather patterns we have. We have quite high interannual variability in terms of weather, which means that in the years that we have quite a large number of periods with very low VRE, the storage makes a lot of money. The years that we don't really have these energy droughts, the storage actually loses money. And the point we are here in the process is that the government decided to introduce a cap and floor scheme. They made this decision in 2024, end of 2024, and now we already have the first application window closing, and 77 projects progress from the eligibility assessment case to the assessment of their costs and benefits. And if all goes well, we will have a few LDS assets online in 2030 and 2033. So the cap and floor mechanism is a mechanism actually the UK has great experience with because they're using it for interconnectors with other countries. The idea is that if you think of this curve here having points for different years in time, some years actually in the beginning, let's say, the revenues are between a floor and a cap, so there's no need for intervention. But in certain years where the specific project be it interconnector or storage, doesn't make enough revenue for the floor, the government, on behalf of consumers, will top it up, its revenue. So they will give it a top-up, and the asset is guaranteed to make the floor. In other years where the project is really successful and it makes revenue above a cap, the government will take back the excess revenue and give it back to consumers. To be extremely precise, the cap is not soft. So it means that the excess revenues are shared between the asset and the consumers, just because we want to maintain the operational incentives for the storage. And what we could do with our models in terms of understanding these mechanisms, of course, we could go ahead and model them, and this is what we have done. But before we do that, we started with a simpler case where we have what we call a complete market, where we assume that all this risk between players and investors could be hedged, with contracts being available, and an incomplete market where we assume that each investor is risk averse, but they don't have a way to manage the risk through hedging contracts. And we compare these two cases, the complete and the incomplete market, because these two cases will basically, the difference between the two will give us an idea of the upper bound of the benefits from an intervention from the government. You could assume that the best case scenario, the cap and floor mechanism would look like the complete market, and the incomplete market is the worst case scenario for describing where the market is today. We have results from these cases with the incomplete market, and a nice thing about these results is when we process them, we can calculate the cost of capital, implied cost of capital, including the risk premium. So you see here that as the risk aversion increases, we see that the risk premium also increases, because at the risk neutral level, we have the risk-free cost of capital. And you actually see that this increase is much higher for long-duration energy storage compared to batteries, which gives some hypothesis that an intervention for long-duration energy storage potentially is a good way to go. So to summarize what we saw from here, we saw that in a net zero power system with long-duration energy storage, the revenue volatility, if you remember these curves, is quite acute. I think I forgot to mention that it was lower for the case with the energy and the capacity market compared to just the energy-only market. But this difference in the width was lower for tire emission limits. And then we also see that the revenue volatility essentially results in high risk premiums for LDS. Where we are now, in terms of our work, we have this forthcoming article that we discussed the policy proceedings in the UK, and we have simulations with various policy schemes. So we have actually done these simulations that we call partially incomplete here, where we have this equilibrium model with different agents, but also a stage where we price different kinds of contracts. And these are the results you should expect to see from us in the coming months. And of course, we're interested also to study the dispatch incentives for long-duration energy storage, both under the presence of a cap and floor scheme, but in general as well. So with that, I would like to thank you very much, and I appreciate this was a very different talk compared to everything else, because we're mostly using aggregation techniques, and then in these simplified models, we study the effects of policy mechanisms and different market designs.